A lot of the missions sent to explore the moon and a lot of the human exploration that is planned for the moon is centered at the moon's south pole. And that's because this is the place where there seem to be large amounts of water, that you've got these permanently shadowed craters at the south pole of the moon. In that, you're going to have water, but not water like a skating rink, not water like a big pool that you can just go and swim in. No, water that's mixed in with this regolith that is going to require some technology to extract it. And when we set up some kind of research station, a base on the moon, they're going to require water. But how much water? Well, my guest today has done the math. So my guest is Dr. Jeff Lee. He's an affiliate research professor at the Center for Astrophysics, Space Physics, and Engineering Research at Baylor University. And he recently published a paper about the water management considerations for a self-sustaining moon base. In other words, how much water are human beings going to require to even just exist on the moon? Both our personal use, our baths, our drinking water, and breathing, as well as our food use, if we're going to try to grow crops on the moon, how much water is that going to require, as well as our technological uses. If we want to cool down supercomputers, if we want to use cutters that are going to need to require coolant, not to mention us being able to use water for propulsion. If we want to be able to hop around on the surface of the moon or refuel spacecraft, all of this is going to require a lot of water, which is going to have to be pulled from those craters. And so in this conversation, we talk about the calculations, how much water is required, how it's going to be extracted, what it's going to be used for, what are some ways that we can reclaim it, and what lessons will this teach us about being able to use water more efficiently back here on Earth. So enjoy this fascinating interview with Dr. Jeff Lee. Jeff, do we have a good sense of how much water human beings will require if they're going to be trying to live permanently on the moon?
We have a pretty good idea based on our understanding of what human beings need on Earth. So, for instance, we know how much human beings require in terms of drinking water, in terms of water to bathe, to wash clothes, and so forth. And the needs of a human being aren't going to change regardless of where the human being goes. You're still going to need to drink such and such number of gallons of water. And therefore, we can at least have a starting point to know how much water a human being is going to need for personal needs for a moon base.
It's funny. This is personal for me right now because I had to we have someone at our house giving us a quote on a water filtration system. And so we actually had to come up with numbers of how much water usage we typically are going to use for the month. And I had to interrupt that conversation to come and do this interview with you. And my wife is still out there providing estimates on water use for our family, which I think is quite funny. But you know, that's like the worst case scenario where you're just like pulling water out of the ground, you're drinking it, you're bathing in it, and then you're pouring it back into the ground. That can't be the most optimized way to approach this.
No. For one thing, the water resources on the moon are limited, much more so than the Earth. The amount of water we estimate to be on the moon in total is about 486,000 acre feet. That is to say, if you imagine a 1 acre square, and we have on that a square column of water, it would be 486,000 feet high. That is a great deal of water, but that is very, very small compared to the amount of water that's on the Earth. The other challenges that we face on the moon base in terms of that water is it's not free flowing and it's not everywhere. About 70% of Earth's surface is covered by water, but only very sparse and particular locations on the moon have water available. The polar regions, for example, in craters, for example, these are locations where you have eternal shade and where water can exist in its frozen state. That water is probably not like a skating rink. It's probably embedded and mixed with the lunar regolith or topsoil of the moon. And therefore, we would have to get that water out of the lunar regolith, put it through a treatment facility so it becomes potable, and then distribute it across the moon base for the human beings who are living there, and for their technical and agricultural needs as well. So it's not as simple as just pumping it out of the ground.
And based on the paper that you wrote, the water that the humans are going to require for their drinking, for their bathing, that's just one part. That just our modern technology is a thirsty business. So what are the other aspects that just maintaining a base on the moon is going to require in terms of water?
The two other general areas beyond what a human being will need for bathing, drinking, and so on, one of them is agricultural needs, and that's by far the largest need, because a human being is going to need about 370 or so square meters of land to farm on. And therefore, if you have a 100-person moon base, you're going to have a fairly large field where you're going to have to grow hydroponic plants. Those plants are going to require water, something on the order of about 6 liters of water for every square meter. And that's going to add up, because you need about 370 square meters for every person. If you have 100 people times 100 people times 6 liters, and therefore it becomes quite a large amount of water that you need for agricultural means.
Now you're giving me that 6 liters. You're not saying 6 liters per month, per year. Is that because you're going to be recycling this fairly efficiently? So it's just as long as you have that water in the system?
We need that water in the system, yes. So you would need the 6 liters of water for every square meter every day. And whether that water was coming through recycled used water or new water, the plants won't much care.
Right. Okay. So we've got the humans drinking their water. We've got the plants drinking the water. And what was the third major use of water?
We would want water available for our technical needs. And therefore, if we have supercomputers that we want to water cool, if we have laser systems that we would want to water cool, any high-tech, high-power drawing electronics that we want to use water cooling for, we would need it for that. If we want to have water available for fire suppression, we're going to have water stored and immediately available for that. Whether water is the best choice for fire suppression on the moon base under all conditions is another question entirely. But certainly, if somebody's bedding catches on fire, we're probably just going to want to douse it with water. And of course, from water can come hydrogen and oxygen. And therefore, from the water that we pump, we can get the oxygen that we breathe, and hydrogen for fuel and laboratory experiment applications as well. So we have the human needs, the agricultural needs, and the technical needs.
And obviously, I think the sky is literally the limit on the technical side. If you're going to try to have, if you're going to build a refueling station, then however much fuel you're going to want to provide to the future rockets, it could be a little bit or it could be bottomless.
Absolutely.
Yeah.
How far one wants to go with this will determine how much water you need. So I have said in the paper, just as a reference figure, 2 acre-feet per year for technical purposes versus 12 acre-feet per year for human needs. But as you say, if you want to start launching spacecraft and using water in a big way, then the technical needs could vastly exceed the other needs.
So that 12 acre feet, I don't know sure what kind of hectare meters that is for me and the other metric people in the world, but it sounds like a lot. And as you said, yeah, and it's not just you're going out and you're just putting a hose into the nearby crater and siphoning in the water. And it's not even that you're just chipping away chunks of ice and bringing them in and letting them melt. It is mixed in with significant amounts of regolith. So do we have a sense of how unready that water is for consumption? How mixed in with the regolith is it?
Anything beyond surface ice would be incredibly mixed in with a regolith. There would be ice crystals, if you like, potentially sifted below the surface tens of centimeters down. And therefore, the method that we propose to get at this water is, like you say, not just sticking a hose and turn on a pump, but we would use heat drills and therefore literally drill a cylindrical column down into the regolith, perhaps a half a meter, a couple of feet down, and then turn on that heat drill using 10 kilowatts or so of electrical power, and that would heat up and vaporize the surrounding regolith. And that regolith would come out as a gas, including the water, the rock, everything nearby that heat drill would emerge as a gas. And if over this group of heat drills that we would need, we place essentially a tent, a dome over it. In that dome, we can collect this water vapor and then move that water vapor from the collection tent into an adjacent tent or dome. And from there, we can begin to liquefy the water. And we'd liquefy the water and we'd solidify the regolith, and therefore what you would end up with would be liquid water and a lot of dirt, for lack of a better word, mixed in with that water. But now we have a very terrestrial problem, is that we have dirty water that we have to treat, and we know very well how to do that.
Right. Yeah. Back to the meeting that I'm just having about getting sediments and various iron concentrations and manganese out of my water. There's as you said, it's a very well-known problem. There are plenty of solutions. It's interesting. I had read some papers where people are sort of looking at the kinds of energy use involved. And if these are in the permanently shadowed craters of the moon, you obviously have no direct access to sunlight. And that sounds like a very power intensive process. Do you have a sense of how much energy would be required to liberate that much water from this regolith ice mix?
Well, I wrote about that a little bit in my paper, in that we would need a certain number of heat drills in order to get enough water ultimately through that method. And if each heat drill was using 10 kilowatts, then we're certainly into the megawatt range. Certainly. What's nice about solar power on the moon is that we have regions of the moon that are lit at least 90% of the time, and we have unperturbed sunlight reaching those regions. And that sunlight is about 1,200 watts to the square meter. And if we call it a kilowatt per square meter, and you assume that we can get 40% of that from a solar panel into electricity, a football-size field of solar panels would give us quite a bit of power. And if we increase that, obviously, we'd have more power. The idea, though, of using a nuclear fission reactor on the moon, much as we use here on Earth to produce electricity, would not be practical for the moon, because we would need 500 or 600 or 700 gallons of cooling water per megawatt hour that we produce out of this nuclear reactor, and therefore using lunar water and contaminating it with radioactive material in order to produce electricity for the Moonbase just doesn't seem like a very wise approach. So solar power, potentially 87 rubidium decay, which is, of course, what we use on our spacecraft to keep the electronics warm, is another potential source of electricity as well, not necessarily for water sublimation.
Right. And I know that there are mechanical ideas about this as well. We reported on some ideas for sorting, say, metals out of the regolith, and the traditional idea is that you take the stuff and you hit it with chemicals to try and separate things out, or you use heat to try and they found that you could actually smash it and you get the crystals forming and then you can start to collect the crystals together, and then you can purify them from there. And so I can sort of imagine, many different ideas will be proposed, or maybe you're going to dig out the regolith, take it out to an area that's in sunlight, see if that will separate it out. There's going to be a lot of ideas to finally settle on what is the most efficient way to get access to that water, because setting up a football field worth of solar panels so that you can run heat drills into this sounds like a big operation.
It would definitely be a big operation. This type of a moon base would not be our first trip to colonize the moon. We probably begin with adobe huts or something of that
Right.
type, but a large structure, permanent moon base housing 100 people, yeah, on an ambitious scale like that, multiple hundreds of square meters of solar panels doesn't become inconceivable. But I completely agree. That's not a short-term approach.
Yeah. So then just getting that water to be the minimum amount that you're going to need in the system will be that first step. So how well does water reclamation get us in trying to minimize the amount that we lose every day, every month?
It depends on the use that the water is put to. The best ability to reclaim water that we've used is human use. In that, when we flush a toilet, for example, we can reclaim the vast majority of the water that we flush down the toilet. And drinking water, we can reclaim that through treating human urine and so on. Agricultural reclamation, though, is much more difficult. We can't reclaim nearly as much through agricultural use as we can through human use. Agricultural use reclaim, we might hit in the 60% range or so. And therefore, we're definitely going to need to have more. We're going to need to have more heat drills based on agriculture than we would based on human use. Technical reclamation is a completely different matter, and that depends on how the water is being used. If we're sending it away on spacecraft or breaking it open to get hydrogen and oxygen, then that water's more or less disappeared from the system.
Right. But I can imagine, yeah, if you're just using it to cool your supercomputer, you just have to wait till the water cools down a little bit and then you can drink it, as long as
Sure.
it's not being
Sure.
contaminated, right? So, like, when I think about people's plans and their sort of sci-fi dreams of being able to go and set up a colony on the moon and live on the moon, and boy, we're just days away from 1 million people living on Mars and so on and so forth. We need water. And how much do you think this level, like, based on you sort of sitting and sort of immersing in the problem for the time that you spent in writing this paper, what is your sort of overall opinion of how feasible and practical or easy is it going to be to actually set up some kind of permanent habitation in space where we have to create an entire closed environment?
Having a completely self-sustained environment on the moon where it can be totally and effectively permanently separated from the mother world, I don't think is going to be possible in the conceivable future. Because on Earth, there are a lot of things that we manufacture and have in abundance that we take advantage of just in everyday life, be it medicines, clothing, Band-Aids, all of these things. If we have a moon base that's going to be completely self-sustaining in that it no longer needs the Earth, something like an O'Neill cylinder that would travel to another star system, taking people with it, that kind of situation is much more difficult than a moon base that we call self-sustaining in large air quotes. By self-sustaining, I mean you don't have to truck in the food or the water. We are technologically able to create a moon base of the type that I have described in the paper, where it would be a series of buildings that would be interconnected. They would have an air supply that would replenish and be filtered. There would be a water supply that would come from the moon itself. and be treated and managed by the people on the moon, and that we could have an electricity generating system that would provide the power of the moon base. Everyone on the moon base would be a vegetarian. They would grow their own food. There would be no meat eaters on the moon, or at least people who wouldn't eat meat very often. But under these conditions, we could build such a moon base or begin the process today. But a moon base that would be completely self-contained and not need the Earth at all is beyond our capabilities for the foreseeable future, I would say, at least reasonably.
Right, right. So what would be sort of the largest pieces of technical uncertainty today?
I think there are a number of uncertainties, certainly technical uncertainties. Getting the water itself and doing as I've claimed in the paper, no one has ever actually done.
Yeah.
We've modeled it. We've used terrestrial analogs and said this is how we do it on Earth, and therefore this is how we could probably do it on the moon. But before anybody starts digging a foundation for a moon base, I would strongly recommend that we have an in situ investigation where we actually go to a place like the Shackleton crater at the South Pole, and we actually dig up the regolith and see if the water is really there, and if it's really there in the amounts that we believe, before we go much further with a moon base. Because if we have to truck the water in from Earth, it becomes an almost forget it kind of prospect.
Right. It's funny, though. We are just, the time we're recording this, we are about 2 days away from the Chinese attempting their Chang'e 6 lander, which is going to be going to the south pole of the moon and scooping up probably 2 kilograms of lunar regolith in this relatively water-rich environment. It's not going to be going to one of these permanently shadowed craters, but it's definitely going to pull regolith from an area that probably has more water mixed in with it than other parts of the moon. And with Chang'e 7, their plans are to actually attempt some in situ resource utilization. Was it Chang'e 8? Anyway, one of the next missions after that, they're actually going to try 3D printing out of lunar regolith and seeing if they can extract water, produce some of these. So it'll be interesting to sort of find this rubber hits the road. Hopefully we'll find an answer from them. Are there any other missions in the works that you're aware of that will actually take some of these practical steps?
None that I'm aware of that are necessarily in the works. The ones that you mentioned, China, are the ones that I'm aware of. The Artemis missions are, to the best of my knowledge, not going to be looking for lunar water specifically in terms of the long-term habitation of the moon. I think those missions are a little bit more generalized toward geology than towards hydrology.
Yeah, Artemis 3 for sure. I know, with some of the other ones, and there are some other lunar landers planned with NASA and with like intuitive machines and so on that could have other experiments on board. So I think, all eyes are on the south pole of the moon, and so it does make sense. I think, how do you sort of, like, after you've gone through this research and you sort of put on your science fiction hat, what do you think the future of human habitation on the moon will likely proceed?
Well, I think that my original passion for the moon really comes from 2 sources, one very real and one very science fiction. The very real one was Apollo 11. And probably my first memory of a world event was watching the Apollo 11 moon landing and thinking, this is absolutely extraordinary. As a little child at the time, I thought that this is the kind of thing that I want to do without being able to articulate what it actually was. But as a slightly older child in the mid-70s, I grew up with Space 1999. And
Right.
that was, I mean,
Now
as
that was a
scientifically,
compellingly accurate,
oh,
scientifically accurate show.
oh yeah, absolutely, as scientifically hokey as that show was in just about every way, I found it incredibly inspirational for me as a young child, thinking, could there really be a human colony on the moon? And is this something that, even in a small way, I could ever have any part of? And that's something that I think, in a way, kind of fueled my science fiction passion. And I think the remarkable thing about that television show, and for those who may not have seen it, that by 1999 there was a permanent human colony on the moon, where shuttling back and forth between the Earth and sustaining themselves on the moon was just a fact of everyday life. And I thought that was an incredibly realistic concept, and to an extent still do believe that such a permanent moon base could be built with the technology we have today. Where the show, of course, became hokey was the nuclear explosion that cast the moon out of Earth orbit to wander the cosmos as this unpiloted spacecraft, and 310 or so maroons, Earth citizens, on the moon base, encountering one very spiritual sci-fi adventure after another. I think that's where the show began to lose scientific credibility. But I think we could produce a moon base alpha of Space 1999 with today's technology, certainly.
So, what about some of the other places in the solar system? I mean, you mentioned O'Neill cylinders, and obviously, all eyes are on Mars as well.
Yeah.
Do you think, does the same math hold if we go to Mars?
Mars is orders of magnitude more difficult than the moon in a handful of ways. Mars, of course, is much farther. It's 9 to 12 months to get to Mars. It's 9 to 12 months to get back. And it's at least 3 months on the surface while you wait for the next launch window so that you don't miss the Earth on the return. So Mars is much farther, much more difficult. Mars has not enough atmosphere to be helpful, but enough atmosphere to be difficult, in that we would be fighting sandstorms on Mars of electrically charged particulates coming in. So building a base on Mars is conceivable, but I don't think we're there yet in terms of being able to do it. I don't think we know enough about building a structure in the kind of hostile environment that Mars is, and having human beings there for a long period of time. I think Mars is conceivable with today's technology and the technology of the near future. Human missions to Mars, where people would land, walk around, explore Mars locally, and come home, I think are very conceivable. I think we can do that. So Mars is exciting for that reason. But again, if we're going to Mars and we're thinking about a Mars base, then we're thinking about the same challenges of the moon. We have to have water. Mars, fortunately, has the polar caps, and we're probably going to end up at one of the poles if we're talking about that kind of a base, or we're talking about pumping water a long distance.
That's interesting. I mean, I think when people imagine a base on Mars, they envision something that's going to be closer to the equator, a place where the temperatures are a little more hospitable. But because the water really is the limiting factor for what you want to be able to get done, it makes the most sense to set up at the poles where, yeah, the temperatures drop incredibly low, but that's probably the place where you can get the most, the water that you're going to need, that really is sort of the engine for the whole thing.
From the point of view of hydrogeology, certainly it's the poles of the moon and the poles of Mars. In terms of other considerations, there may be better locations, but not better locations when one is considering hydrogeology.
Yeah. So it feels like all of these artist illustrations of what a Mars base is going to look like, they should all be, it's set up at the polar ice cap. Like, it should be built on top of ice because that's what you need.
Or near the ice.
Yeah. Yeah.
Might
Right on the
be.
edge of a glacier.
And if we say, okay, well, we don't want to build it there, we'd prefer to build it close to the Martian equator, then my response is, okay, that sounds good. Now, we're going to need a pipeline that's going to go for a quarter or so of the Martian circumference that will get us from the poles to the equator that will pump the water.
Right.
And that's a long pipeline to service.
Right. Yeah. In a place that eats a high percentage of the spacecraft that attempt to land there at all.
It
Like
does.
it's a tricky place to do work.
It's conceivable too when one's going to the moon. You go to the moon in 3 or 4 days. Martian round trip time is, I mean, we're talking a couple of years, essentially, 2 years, give or take. And I can just imagine somebody on the route to Mars needing a root canal. That would be a little bit of a problem. Somebody on the moon needs a root canal. Worst case scenario is they bring the person back to Earth. Again, this would have to be a service that would be offered on a Mars base that wouldn't necessarily have to be offered on the moon base.
I like that idea that when you think about humanity's future of us going to space, the fact that we have this moon that is relatively large, has these resources there available to us, that is just a 3-day journey away, feels really fortunate. And like Mars is cool, but we definitely have a lot of lessons to learn first, starting out nearby.
And that's my feeling. I feel that Mars is an extremely important destination and one that should be pursued and explored. Absolutely. I think a Mars base on the scale of a moon base is premature. I think we haven't done the easier thing yet. We haven't proven that we can actually do this. I figure let's prove that we can walk, then jog,
Yeah.
then run. And
Yeah,
eventually maybe we'll sprint.
Yeah, I say we spacewalk before we space run.
For sure.
Well, Jeff, what are you obsessed with right now?
Well, the paper that I wrote in this field in my geology group at Baylor University, we put this paper together, and the next area related to this that we're interested in is not using what we know on Earth to figure out a moon colony, which is what this paper is. It's using what we understand now about a moon colony in terms of what does that teach us about water management on Earth, particularly in more arid regions of the planet. Growing up near the Great Lakes, I never thought twice about water, but somebody who would be growing up in the middle of a desert somewhere probably has water on their minds in a way that's different than what I did. And so, what can space teach us about the Earth, I think, is our next project related to this. Beyond that, I'd be interested in knowing something about the acquisition of water, the distribution of water in a 1/6 gravity environment, because the moon, of course, only has 1/6 of Earth's gravity, and Mars only has 2/5 of Earth's gravity. And we don't know a great deal about working in those lower gravity environments.
Like, I wonder what a bath would be like in 1/6 gravity. It would be very peculiar.
Would be different. Water would flow at different rates. And just the physiology of the human body exposed long term to 1/6 gravity, we don't understand very well. We understand Earth gravity, certainly, and we understand microgravity because of the International Space Station. But we don't understand much about what happens to a human being who lives for a year or two in 1/6 gravity or in 2/5 gravity. And these are areas that I think would need to be explored by the people who are experts in those fields. I'm interested in water flow in 1/6 gravity. it won't be as difficult to make it flow because we don't have to fight gravity to get the water elevated, for example. But then again, we don't have gravity to help us the same way when we want the water to come down from an elevated height. And how does this affect the technology for water delivery, for instance, water recycling? These are things that we really don't know a great deal about yet, and I think it's worth exploring.
It's interesting. Like, I wonder how much of our water processing does rely on gravity. When you think about, on the one hand, you've got gravity pulling things down. On the other hand, you've got surface tension that's fighting against that gravity. You've got various processes that are filtering, that are distributing water, pipes. A lot of that, like in my city, pretty much the entire thing is gravity fed. We have a reservoir that is higher altitude than the rest of the city, and all of the pipes are filled, big pipes that come down, and everything is just spread out purely through gravity. I don't even know if there's any pumps that are boosting it back up again. And so I wonder how that changes in 1/6 gravity. I mean,
Yeah, absolutely. And
yeah.
this is something that we can calculate, but it would also be something good to model, to look at how the equipment will function and produce the water that we need in 1/6 gravity.
Yeah, yeah.
We certainly don't know this experimentally.
And I think, like, if we can demonstrate improving, really get to know it in 1/6 gravity, especially like the effect on the human body, what happens to a human being in that kind of a lower gravity environment, then that makes, if it's fine, if it's all fine, like, oh, turns out human body, like, yeah, you become a little less bone mass, but overall your health is fine. It's not anywhere near as bad as it is in microgravity. Well, then that just sets us up for success when we do go to Mars, because we know it's going to be in between. It's going to be better than the moon, not quite as good as Earth, but it's going to be probably, if we can become accustomed to the lunar gravity, then that gives us a fighting chance for Mars.
Absolutely, I would agree. I would say that if we can manage lunar gravity, we can manage Martian gravity.
Yeah, yeah.
The other way around doesn't imply. Although I would suggest that if we could manage a base on Mars, we could certainly manage a base on the moon. But
Right, but it's farther.
That's a little bit like saying if you can jump 10 feet in the air, well, then certainly you can jump 5 feet in the air.
Right. Yeah. Yeah. And I do think that all of the other parts of living on the moon, like the moon is more hostile. The moon has less atmosphere than Mars does. It probably has, it has a worse radiation environment than Mars would, because it has no atmosphere. And so if we can develop all these techniques and perfect them on the moon, which is close by, you can swap in new parts and so on. Then when you do want to go to Mars, you've already existed in a much more difficult environment. And then again, that puts things on a little bit of an easier, where things are going to break, where they're going to bust, and they're back within your tolerances.
Sure, sure.
Yeah.
It's something that we haven't touched on, which is a field of great interest to me, is the asteroid impact hazard. Mars has that thin little atmosphere. However, it does protect the surface against small impactors, not against large ones. The
Right.
moon, of course, has no such protection, and therefore the moon base, any solar panels out on the lunar surface, any water collection domes would all be subject to impacts by micrometeorites and potentially slightly larger meteorites when they are unlucky enough to be hit by one. And therefore, that's a concern and a consideration. How do we protect our moon base and the water collection facilities by extension with what kind of technology against micrometeorite impacts? Because that's a concern. On Mars, the concern is different.
It's just another one of those things that we take for granted that the Earth is doing, providing us a service, is providing us security from space rocks to be below a certain size, several meters across. They are blocked entirely by the Earth's atmosphere. It's just
Pretty
another
much.
service that the Earth is doing for us. And I think, we just don't realize we have this sort of, we just don't realize how much of these services the Earth is doing for us in providing us air to breathe, water to drink, ground to stand on, gravity to pull us down, protection from radiation, protection from meteorites. I mean, when we decide to go to space, we are going to have to give up all of those and do it ourselves, which is a tall order. And yet it's what's next.
It very, very much is. We have to give up all of those, and at the same time, we have to find a way to take all of those with us.
Yeah.
Because our needs that the Earth satisfies, of course, won't stop being our needs when we leave the Earth.
Yeah. And I find it exciting. Like, I think those challenges are the kinds of things that I hope will bring out the best in humanity, that we will learn those lessons. And as you said earlier, we can apply those lessons back to Earth when we realize, oh, here's a better way to filter our water. Here's a better way to grow food, because we had to do it in the most extreme environment. Now we have better lessons on a more forgiving environment.
Yeah.
Well, Jeff, it was an absolute pleasure to talk to you. Super fascinating. And hopefully we get to chance to see these experiments performed for real in the future.
That would be amazing if we can, because that Moonbase is something that I think is going to happen eventually. I don't think there's much question of if, but whether that's going to happen within the next 10 years or 50 years or 100 years, I think really depends on how much people want it.
Yeah.
If we want it enough, we'll be able to do it.
Yeah. Well, thank you for your time.
Thank you so much.
I hope you enjoyed that conversation with Jeff Lee about water use, both on Earth, the Moon, maybe Mars, other places like that. Now, I'm going to talk some more about human exploration of space, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrew Gross, David Giltonan, Dennis Alberti, Dustin Cable, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Modso, Paul Rohrbach, Stephen Krasaki, Stephen Fowler-Munley, and Vlad Shiplin, who support us at the Master of the Universe level, and all of our other supporters on Patreon. Like many of you, I am absolutely fascinated by the potential for humanity's exploration of space. It's what's next. I mean, we've explored Earth. Space is the next place that we're going to explore. And yet, when I think about all of the technologies that we use on a day-to-day basis to be able to just survive in space, like, the list goes on forever. What about your medicine? What about various technologies that you depend on? How are we going to get those? We exist at the very end of this gigantic supply chain that is pulling resources across the entire planet to deliver us the kinds of things that we need at the time that we need it. And to then take that technology and extend it out onto a place like the Moon or even Mars is a monumental undertaking that gives me a headache. And so we need ways that we can try and step forward bit by bit by bit. And like, I know a lot of people want to just go to Mars and just like, let's go straight to Mars. We should be living on Mars, on our Mars base. But I really love the fact that we have this giant satellite orbiting Earth that is so close, a place to test out all of these ideas, a place that we can go and resupply, replenish, and even evacuate if there are problems there. So I'm so grateful that we have the Moon, even when I'm trying to use my telescope during a full moon. I'm still grateful that it's there. And I know that it's going to be that place that we're going to be going to next. And I sort of imagine this future. Like right now, when you see the International Space Station fly overhead, and you're like, okay, there's people on board right now. And there will come a time in the near future when we look at the Moon and we say, there are people right now on the Moon. I can't wait. All right, we'll see you next time.